So we're at a place in this class where we are representing particles as waves or as a wave function. And we don't really see waves when we see particles. I mean, if we look closely, they have particle-like properties, but it's not that we see a wave in the same way that we see a light wave or a water wave or something like that. And so we need to think about how we represent the particle wave. So we're going to go back to something which we may or may not have discussed in introductory physics, or you may or may not have learned in introductory physics, but that's the concept of intensity. Intensity is when a wave is incident on your eye, you see the intensity of that light. The intensity goes as or is proportional to the amplitude of the wave squared. For example, if the wave is an electromagnetic wave, the amplitude of electromagnetic wave is going to be the magnitude of the electric field or the magnetic field, right? So amplitude is going to be E or B, and the wave function that represents an electromagnetic wave might be, omega t plus. Oops, hold on. Or that better. We haven't really discussed how you represent an electromagnetic wave in a function, but electromagnetic waves are waves. They the electric field and the magnetic field oscillate, and it turns out that the electric field and magnetic field are self-propagating. We've talked about that before, and typically you'll have you will have an electric field and a magnetic field. This is meant to be in 3 dimensions, which are perpendicular to each other. So if the electric field was oscillating in the XY plane, then the magnetic field would be oscillating in the XZ plane. Yeah, XZ plane. And each of those components, and it's self-propagating, right? The changing electric field makes a magnetic field, which is changing, which in turn creates an electric field. That's what an electromagnetic wave is. And each of those components of that wave, right? One's supposed to be magnetic field and one's supposed to be electric field, oscillates perpendicular to each other. That's neither here nor there. That's just a reminder of what an electromagnetic wave is. The amplitude of the electromagnetic wave, you can see, is either E or B, depending on which component of the wave we're looking at. And we have, or we know, and maybe we haven't discussed, I certainly realize that, but that the intensity of a wave is proportional to A squared. Intensity is basically what we see. So that's what's important here. In an earlier section in chapter 5 that we have not gone over, the author goes into detail to show that the intensity, if you treat an electromagnetic wave as a photon, an electromagnetic wave as a bunch of photons, particles instead, you can show that the intensity is proportional to n, which is a probability. It's the probability of finding a photon in a certain position. Also, it is known as the flux of the photons, but it is a probability of being able to observe the photons. So what I'm trying to show here is that that if you relate the two, that this kind of probability function has to do with or is proportional to amplitude squared, right? So therefore, the probability function is proportional to the amplitude squared of the electromagnetic wave, the probability of finding photons. The reason why I'm going through this hand-wavy explanation is because what this brings us to is how we represent a particle as a wave. We represent a particle as a wave. We use a wave function. We've already discussed that. In quantum mechanics, we represent particles with a wave function psi, which is in 3 dimensions. It's dependent on x, y, z, and t. Of course, we were always doing 1-dimensional wave functions. But this wave function is just an amplitude. And so the probability of finding the particle in a certain place, which is known as the probability density, must be proportional to the amplitude squared, psi squared. So that's the conclusion that we need to come to. Or this is sort of a bit hand-wavy. This is quantum mechanics, and this is the start of quantum mechanics, is that this concept of the wave function that represents the particle, it represents a probability density. Probability density is proportional to psi squared. Now you often see absolute values around this, but that's psi squared. I don't think I've actually really proved anything here. I'm just talking about the way the wave function has, in quantum mechanics, it's been developed to represent this probability density. And the probability density, just to be clear, is the probability of finding the particle in a given volume at a certain time. Now, psi itself, the wave function, can be real or complex. Psi squared is a real value. The probability density is a real value. Psi can be a complex function. Assume that you've learned about complex numbers at some point in mathematics. Certainly not going to teach you them here, but that means that psi squared is actually the complex conjugate of psi. Well, I mean, actually I can, right? If you have a function which is complex, it's got an I in it, the complex conjugate, you turn all your i's to minus i's, right? So if you've done it before, now you remember it, right? So for example, if you have a wave function which is has a time dependence, amplitude a, e to the minus kx, sorry, kt, that's wrong, sorry, omega t. If the time dependence of your wave function, so this might just be the time dependent part, has some amplitude a, and it's got a time dependence of e to the minus I omega t. Therefore, the complex conjugate of that is simply a e to the I omega t. Complex conjugate, just turn all your i's to minus i's. And then, since this is a probability density, which is the probability of finding the particle in a given volume at a certain time, it's probability per unit volume. Therefore, the probability of finding a particle in that volume, the probability of finding a particle in a volume, small volume dV, is just psi squared dV. So probability density, in case it wasn't clear, probability per unit volume. So to find it in a certain volume, dV is psi squared dV. What's the probability of finding it somewhere in space? This is the probability of finding it somewhere in space, right? A given particle, if it exists, must be somewhere, right? So if we want to know what's the probability of finding it somewhere in space, then any space, then we can integrate over all space. And so what should that probability be? That probability should be 1, right? Because it's got to be somewhere. What does that tell us? You might say, well, duh. What does that tell us? What that actually tells us is it tells us how to find the amplitude of the wave function. It gives us what's called a normalization constant. A useful thing to be able to normalize a wave function. We'll do an example, hopefully, to show you what that means. But all we're saying here is you got to be able to find the particle somewhere. The probability is 1 that it's somewhere. Okay, just as a example, let's just say that we know that a particle is constrained in one dimension to be within a length of d, and that the wave function representing the particle is, as given, psi x. This is just an arbitrary function. Just throwing out here, 0.5 cosine pi x over d. What is the value of d? We're just pretending that's the wave function that represents the particle. What is the value of d? So we're going to use the normalization in order to figure out the value of d. So meaning that in a sense, the wave function is already normalized. By normalizing, we have said we have integrated over all space and said it equals 1, and that is perhaps how often how we evaluate what the amplitude of the wave function is. But we're sort of going backwards. We're saying we know the wave function. Let's use the normalization condition in order to determine how much it's localized. It's not how much it's localized, but the fact that we have constrained it to be within a length of d. What is d? So in order to answer this question, we can just use the normalization condition, right? That's psi squared dx is equal to 1 if we integrate over all space, but we know that it's between 0 and d, so all we have to do is integrate from 0 to d, and so therefore we can say 0 to d of 0.25 cosine squared pi x over d equals 1. So we need to do that integral. So evaluating this integral, I'm just going to be careful and say do a substitution. In order to do the integral, of, oh well, let's pull the constants out, 0.25 d over pi integral of cosine squared. That was supposed to be an s since it is substitution. S ds equals 1. To do that integral from 0 to d, we would have to do it by parts, do the figure out what cosine squared equals, and I'm sorry, it would be a cosine times cosine ds, and we could integrate by parts, but also it is valid at this point to just look up that integral. So we get integral of cosine squared, we get what's in the brackets here, and I wasn't careful over here. We're still evaluating from x equals 0 to x equals d, but we made the substitution for s. So if x equals 0, then s equals 0, so we're evaluating from 0, and to x equals d, that's s equals pi, so we're evaluating from 0 to pi. Evaluating from 0 to pi, end up getting that, we plug in the limits, and so in the end we get 1/8 d equals 1, so d equals 8. So it's whatever units we were in, d equals 8. That's a quick overview of the concept of the wave function being a probability function and normalization of a wave function.